Hi, it's Charlie Zeiss with Stargate Pyramids and the Pyramid Science Foundation. Um, Today is a continuation of some documentation that I've been putting together about the existence of universal Phi scaling in the context of fluid dynamics. And I've done a lot of videos showing that contemporary technology in this arena, from airplanes to boats and submarines and torpedoes and bullets and animals and so forth, all have this a unique universal Phi scaling geometry incorporated. And the purpose of it is to increase speed, to minimize drag, to increase fuel efficiency, to minimize turbulence and increase what's called in fluid dynamics laminar flow. So what I haven't done, and this is what this segment is about, is to show you that all of this information that we have spent the last century literally recreating actually existed in the ancient artifacts that we have of ancient aeronautics equipment from our past. So it's a fascinating discovery to find out that this information was known in the past, and yet we lost it in some fashion over the last 100 or so years, and it brings into play a lot of questions as to why this technology and this information got lost in the intervening period. But for a lot of you, this information may be new, so I'm going to go through and give you at least a brief update of some of my prior information, so it'll give you context that will allow you to see this information in these ancient aeronautical artifacts. So we're going to start here. Here's a couple. This is the thumbnail from the video. These are a few of the things that we're going to be talking about today. You can see these various aeronautic objects, and each and every one of them has this geometry inside of them. So first, I want to tell you what universal Phi scaling is, how I got to it. I am starting and still do make meditation and healing pyramids for public sale. And they're designed off of the Russian pyramids that were built by the Russian government and the research director, Dr. Alexander Golod, over the last 30 years or so. Their information about how they came up with this geometry and in fact the geometry itself and the research results were all suppressed, and we weren't able to be published in the West. But I was able several years ago to figure out the geometry, and that's what has begun my quest to find this in nature and in technology. So I've got 5 diagrams here. On the left, you see the Russian pyramid. I have used a protractor app there, as you can see, to measure what's called the slant angle of the pyramid. And I knew what that was, but I needed to sort of reverse engineer how to get to that number. And the way I did that, if you go over to the 2 diagrams on the right, the one on the left shows a series of circles. The beginning diameter stacked on top of each other. The bottom circle, you could do this in 3 dimensions as well, and that would be a sphere. But start with a diameter of 1, and you divide the diameter of the next sphere on top by this golden ratio itself, which is 1.618. It's nature's universal scaling process and number. Researchers Nassim Haramein and Dan Winter have proven that the whole universe is scaled in Phi. So this was kind of why I decided to try this. And sure enough, when you do that process and you stack circles on top of each other and divide the previous diameter by the golden ratio, you get this series of circles or spheres. You can build in 2 dimensions a triangle around it, or in 3 dimensions a 4-sided pyramid, and you're going to come up with these geometric angles. You can see in the right diagram, 76.345 degrees, ... is called the slant angle, and 27.309 ... degrees because this is based on an infinitely irrational number. Well, that's what's called the apex angle. So we're going to be focusing most on this top angle of 27.309 degrees today in our discussions. But either one of those can be used to identify this universal Phi scaling process in nature and technology. So here's some other examples of universal Phi scaling in nature. Light refracts at this geometric angle. We can't see sound, but we can measure the geometry of the megaphone that we know will amplify the sound, and it's the same number. We can find this in water vortexes. We see it in our DNA, a very, very fundamental place, an important place to recognize the significance of this geometry. We can see it in tornado funnels. This is a topic for a separate discussion, but I've done other videos suggesting that this geometry is the key to implosion free energy technology. But now to go to the animal kingdom, we see, and this is the water examples of fluid dynamics we'll be talking about in a minute. This is an example of one of the fastest swimming, sea creatures, the great white shark. And we see that this geometric angle shows up in the front of the fish. It shows up in the back of the fish. And if we look from the underside, we can see that it's in the snout of the great white shark as well. So this is an absolutely fundamentally important geometric angle. You'll see it in all fish, and especially the ones that swim fastest in the ocean. Now, birds, the peregrine, which is the fastest diving bird on Earth. You see, once again, this geometric angle in the front. You see it in the rear, and you also see it in the angle that the bird uses in its dive to go catch its prey. So again, fundamental information here, but it's in nature, and that's why when we see it in technology, we need to understand the purpose for its existence. Now we're going to get into fluid dynamics for just a minute. This is a segment of mechanical engineering that deals with objects flowing through a medium such as air or water. Aerodynamics and hydrodynamics are both kind of subcategories of the general category of fluid dynamics. Now, in this particular example, we've got a sports car that's being tested in a wind tunnel, and we can see that these wind tunnel tests that the air is not turbulent, and in fact, it's sort of bending very nicely around the geometry of the automobile. And the reason for that is this is called laminar flow. This is maximizing laminar flow and minimizing what's called turbulence, which is just a disruption of the smooth flow of air. And you want to have fluid dynamics and maximize in fluid dynamics, you want to maximize laminar flow and minimize turbulence to maximize speed, fuel efficiency, and also to keep the car stable on the ground. Now you'll see the 27309 geometry in the back of the automobile, but you don't see it in the front. You see 13654, which is half of that angle. If you'll see, they didn't try to optimize the fluid dynamics on the bottom of the car, because if you were to do that, you'd get lift on the car, and so it would be unstable at high speeds, and you couldn't go around corners very well because you wouldn't have a firm, you wouldn't have a grip on the road that you need to make sure that you can get through the turn. So you're going to see the 13654 sometimes, and sometimes the 27309. Now, just a quick description of drag force. This is the equation that has been devised for drag force. And of course, what we wanted, drag force is equal to 1/2 of what's called the drag coefficient times the density times the square of the velocity times the area of the object. Now, the things that we're most concerned about here today are velocity and the drag coefficient. Now, the drag coefficient is really what we can control in any fluid dynamics environment. And engineers, as I say down here, are not able to make precise calculations of drag coefficient. There are ways of estimating drag coefficient through what are called computational fluid dynamics modeling programs. There's over 200 of these that are out in the marketplace. So you can see what a robust market it is for this kind of fluid, this information. But the only current way to really accurately determine drag coefficient is from wind tunnel and water tunnel testing. However, as we're going to see in a few examples, both current and ancient, even though universal Phi scaling and sacred geometry aren't taught in our engineering programs, it is the foundational principle required for minimizing drag coefficient in all types of fluid dynamics environments. So keep that in mind as we move forward. I'm going to be next showing you here an example of the Airbus 300 commercial airplane. I have done this research on every single jet airplane that has ever been a commercial plane that's ever been manufactured. And every single one of them has this geometry in its fuselage and in other places in its aerodynamics. And yet, to my knowledge, engineering programs aren't even aware of the principles, the sacred geometric principles that underlie these geometric angles. But you can see here's an example of a goose, and you look at the rear of the airplane and they look like a virtual match. Now here's some other examples from contemporary aircraft. We'll see that both from a top view from the front and the rear of the aircraft, that we see this geometry at play as well. And interestingly enough, I don't know the correct engineering term for this. I'll call it an offset to a perpendicular of the wings to the fuselage, uses this 27309 geometry seemingly as well. So now let's start to look for these things in ancient flying technology as depicted in artifacts, drawings, carvings, and the like throughout history. These are carvings from what's called the New Kingdom Temple in Abydos, Egypt. Many of you may have seen these before on Ancient Aliens or other types of programs, showing these ancient vehicles. Some look like submarines or boats and helicopters and so forth. And sure enough, when we go to measure these geometric angles, we'll see in this case, this angle that our object that I'm pointing to now, we're measuring, and we see that geometry both in the front and the rear of that vehicle, as well as the offsetting 27309 degree geometry in the vertical stabilizer on this craft. So they clearly knew about this as well. It's not an accident. When we look at the helicopter, we see once again, now we're seeing the 13654 because the bottom of the helicopter is flat. But we see this geometric angle once again showing up in the front and the rear of this helicopter carving, as well as the 27309 angle in the vertical stabilizer. So this is, you can't tell me that this is an accident. These were technologies that existed. These angles are precise, so they knew that these principles were necessary for stability and proper aerodynamics. Now here's another example from Egypt. This is an artifact that was recently uncovered, I'd say within the last, I believe, 50 years, of the Saqqara bird. When I say uncovered, it was in a museum for, I think, over 100 years until someone recently looked at it aerodynamically and said, this could be something more than just a bird carving. This could have been a prototype for a vehicle. Well, whether it is or not, As we've seen, the birds have these geometries as well, but we'll see this geometric angle in the tail of the bird, both in the rear and also in the body as it comes back from the front. So I don't believe that these are accidents. We'll see it in the wing of the bird, and also in the same geometry, same point of a drawing that was done by a professor who did extensive research on this artifact. And also from his drawings, we're able to see from the top-down view that we see this geometry both in the front of the craft and also in the rear. So this geometry is cooked in everywhere that we're able to find it, just as we did on the commercial aircraft. So my feeling is they actually did a test. Someone built a model of this and flew it successfully, given these specifications, and it was aerodynamically sound. So I think there's this is not an accident. Here's some other examples. These are the Kimbaya artifacts from Colombia. This is a group of 18, I believe these were made from gold, objects which look like flying objects. And I just want to talk to you about a couple of them that I looked at. This particular artifact, once again, we're going to see the aerodynamic 27309 geometry in the front and in the rear of this craft, as we do this offset to vertical in the vertical stabilizer. So we're seeing this geometric angle in so many places. Now here's another craft from this set, and this one shows you the 27309 offset to perpendicular in the angle of the wings of the craft. So again, these can't be accidents. And finally, this is the horizontal stabilizer on the same artifact that we saw in the previous picture, and we see the 27309 angle in the tip of the horizontal stabilizer as well. Now here's another Indian artifact of a flying machine, an Incan craft, and we see that we find this geometry in the nose cone of that vehicle. Here's a Mayan alien artifact that demonstrates this geometric angle as well. And here's some from India. Many of you have heard of the Vimanas. These were ancient flying machines that supposedly existed in ancient India. Here's a particular version of that flying machine with this geometry. It's called the Shakuna Vimana. And again, it doesn't seem like it could be a mere coincidence that all of these objects have this same geometric angle. More details about these ancient Vimanas can be found in this book, the Vimanika Shastra, which translated means the science of aeronautics. So there's a lot of information in there about this geometry and others and how to build these craft. This book was written about 100 years ago. Another book from India giving information about ancient flying craft is the Mahabharata. Interesting to me that once again we see an object with the 27309 geometry on the cover. Now here's an example of an artifact called from an area called Toprakale. I don't know if I'm pronouncing that right. This was part of the ancient kingdom. This is a town or an area which was part of the ancient kingdom of Ararat, which is in contemporary Turkey. Now, the artifact itself is in the top picture, and in the bottom is an artist's depiction. Parts of this have been broken off, and so they attempted to devise, their own depiction of that. But in either case, you can see that this 27309 geometry is showing up in the nose cone of this vehicle. We can see what look to be, rocket engines of some sort in the back of this craft. So once again, we're seeing this geometry in other places in the world in ancient flying craft. So I want to now go to a few of the more contemporary examples that I found. 17th century Lithuanian rocketry pioneer called Kazimierz Siemienowicz. This was a rocket diagram that he had. He was using this geometric angle for his rocket designs. And here's a rocket that was actually used and developed by the British. It was called the Congreve rocket. And it was used against the US in the War of 1812. So again, all of this sophisticated knowledge of aerodynamics is showing up in these ancient rocketry designs that we have had to essentially redevelop and reconfigure in more recent times. So now that brings us up to the current day, and I wanted to show you this in perhaps the most vivid and important example of the importance of this geometric angle in contemporary technology, and that's in the development of hypersonic vehicles. Now, Russia is the lead country in this. They're ahead of all other competitors. China is catching up, and I guess we're in third place, but at least according to published, available sources. And I wanted to show you this rocket has been used. These hypersonic vehicles have been used in the wars in Ukraine, but you can see that this hypersonic glide vehicle incorporates the Universal Phi Scaling geometry in the development of its of the body design. Now, if we go back and think about what that equation on drag force that we looked at earlier, you know that the drag force is a function of the square of the velocity. So the importance of geometry in this, in minimizing drag, is critical to keeping these planes flying and also from not burning up in the atmosphere. Because if the geometry isn't right, there's going to be a tremendous amount of heat buildup on the craft. Now, that can be mitigated through geometry, and it also can be mitigated by advanced metallurgy and material science. But I just wanted to show you that the Russians, whose device is successful, uses this geometry. However, the geometry of the US devices, this one was tested about 10 years ago, didn't. And what happened to it? It burned up in the atmosphere from overheating. Now, I'm not an engineer, but I'm going to suggest that this may have been a significant factor in this design not working and burning up in the atmosphere. Now, I will tell you that the current generation of hypersonic vehicles that I found on the internet that the US is developing have copied the Russian design and are now using this 27309 geometry, just like the Chinese and the Indians and the Iranians, who have all developed hypersonic, have advanced hypersonic technology. So just showing you this ancient technology, knew about this geometry. It's showing up how critical it is in contemporary technology. It's used in contemporary technology. So to say that these ancient artifacts were that the builders of that these craft, or that the knowledge to make these craft didn't exist in these ancient cultures is refuted by the fact that this geometry is found in numerous cases in these ancient artifacts and designs for these vehicles. So I hope this information has been helpful. I am planning on taking this information along with all of my other documentation on the use of universal Phi scaling in fluid dynamics and making a documentary into it. If there are any of you out there who happen to see this and have access to fluid dynamics, computational fluid dynamics programmers or companies, or engineering firms that might be open-minded enough to actually adopt these kinds of concepts into their modeling, please contact me at charlie@stargatepyramids.com. But that's the real purpose of this upcoming documentary, is to get this information put together, show people that this has been part of our technological heritage, and somewhere or another, we just sort of lost track of a lot of it. So trying to get the world to a better place where we can design our technologies with the best information available. So I thank you for watching, and you have a great day.